Hello everyone, thanks for your interest in our paper. It's Rui Li from University of Science and Technology of China. It is my great pleasure to present and share our work. The title of our work is Learning Fine-Grained Features for Pixel-Wise Video Correspondences. The code of this work is available on GitHub. One of the most fundamental problems in computer vision is learning visual correspondences across space and time, which can be divided into three categories according to the granularity, including object-wise, group-wise, and pixel-wise correspondences. Learning representations from videos is one approach to finding the correspondences. Researchers have been exploring different self-supervised methods for learning generalizable representations using unlabeled videos collected in the real world, including cycle consistency-based and reconstruction-based methods. Despite obtaining promising outcomes, current research has predominantly emphasized performing object-level or patch-level similarity learning, making it difficult to accurately recognize pixel-wise differences with the learned features. At the same time, there is another line of work approaching video correspondences by deterministically predicting the displacement of each pixel, which is known as optical flow estimation. In recent years, approaches use synthetic data with supervised learning for flow estimation, which show a superior ability to find fine-grained correspondences. However, in real scenarios, these methods often show lack of robustness on real-world videos. In this paper, we facilitate fine-grained feature learning by integrating self-supervised learning on unlabeled videos into supervised learning with labeled synthetic videos. Given a pair of video frames, we consider the position at which the pixel I is transported to the second frame in a local range obey a probability distribution, considering the nature of temporal coherence. Then, the discrete probabilities can be approximated by normalizing the feature similarities computed between query feature at pixel I and candidate features in the local range. Our goal is to learn a fine-grained feature space with the encoder by designing different learning objective functions for the probabilistic mapping. Labeled synthetic videos are often used as supervision for learning the optical flows in recent studies. Given a pair of rendered video frames, the synthetic data already provides pixel-wise motion vector. A valid question then emerges as how to learn features using such deterministic correspondences. The most straightforward way is to directly convert the motion vector to a Dirac distribution for the mapping. However, the query pixel varies smoothly over space and time, which indicates a more soft distribution. Thus, we devised to generate the probabilistic map with Gaussian distribution. However, the Gaussian prior only considers the Euclidean distance of coordinates, which shows limited capability of modeling the complicated distributions. We further decouple the spatiotemporal correspondences into time and space dimensions, and believe the synthetic supervision already provides valuable temporal cues. The soft distribution over space dimension can be approximated by computing the self-similarities for pixel j within the local range using the pre-trained strong 2D visual encoder like MoCo, Dino. Then, the learning objective function defined as Kullback-Leibler divergence between the predict distribution and labeled distribution. Table 4 shows the performance comparisons across the three kinds of objective functions. Expectedly, the proposed soft labeling gets the best performance. Meanwhile, we observe there exists notable gap between the synthetic and real videos. The learned features show unsatisfied generalization ability in real scenarios. Inspired by recent studies, we try to improve the learned fine-grained features by introducing self-supervised feature learning into the framework. As observed in the figure, the pixel repetition encourages us to learn the fine-grained features by reconstructive learning. More specifically, the query I can be reconstructed by a weighted sum of pixels in another frame in the local range by using the pre-computed discrete probabilistic map. However, the pixel repetition does not hold for pixels that become occluded, thus, we exclude occluded pixels from the reconstruction loss by forward-backward check. Next, we further improve the fine-grained features by introducing the network a gradient reversal layer. We additionally train a discriminator to identify whether the probabilistic map comes from synthetic or real videos, which helps to learn domain-invariant patterns. The overall training objective is formulated as a summation of proposed three losses. The Table 5 shows how each component impacts the overall performance. The results consistently indicate that incorporating self-supervised and adversarial training with unlabeled data exhibits a performance boost against the model only trained with synthetic data. We also propose a course-defined framework for efficient probabilistic mapping. More specifically, we first obtain coarse-grained matching and then upsample it to get the fine-grained result, which avoid dense matching on high-resolution features. The whole framework is jointly optimized in an end-to-end manner on Flying Things and YouTube VOS. After training, we directly utilize the pre-trained model as the feature extractor without any fine-tuning, and leverage the algorithm of label propagation for inference on downstream tasks, including point tracking and semi-supervised video object segmentation. Here are the quantitative results for point tracking. Our method achieves significant improvement against its counterparts. More surprisingly, without any specific designs, our performance even surpasses ASK-specific methods like PIPS and TAPNet. We give some qualitative results for point tracking. Our approach can output more smooth and accurate trajectories close to the sparse visualized ground truth, even facing dramatic appearance changes and deformation. For video object segmentation, our method produces tight boundaries around the object areas and obtains more fine-grained results, especially for small objects. Thank you for your listening.